Okay, so now let's put the maths hat on. Okay, and we are going to discuss so-called Green's identities. Okay, and there's a little historical info block in the online notes. Please have a look at it, because George Green was a cool chap who essentially was a miller, not an academic, but at some point while he was doing his stuff, he had an idea about, oh yeah, Green's functions, and then yes, solutions to Laplace equation, and yes, like propagators and whatnot. And he wrote this essay from nowhere, which to this day perhaps remains the most amazingly useful contribution of mathematics to the theory of electrodynamics. And we will see just some basics of what he did here. So what's the objective? It's to make a precise statement about the existence and uniqueness of solutions to Laplace. Okay, so just let me entertain you with this reasoning in the last 5 minutes that we have. Okay, so what are we going to do? We're going to start from the divergence theorem. So what do we say? We consider a certain vector function f. We have an integral over a certain volume, d tau, and I've got the divergence of this vector field f, which I haven't specified yet. Okay, and what is that? According to the divergence theorem, it just tells us that this is the integral of dA dotted into let me actually write it even in the following way. dA f dotted into the normal unit vector at this position there. That's where we start from. Okay, and now we're mathematicians. We do nonsensical choices that transpire to be good choices around. So choose for this f the following representation. I'm going to say that it's a scalar function multiplying the gradient of another scalar function, phi and psi. Okay, both phi and psi are scalar fields. All right, so then what do we do? We just write the divergence of that object here by applying the kind of identity that this is just like phi. So I can act with the divergence on this gradient here, so then it becomes the Laplacian of psi. But then there's also the grad phi dotted into grad psi. Okay, and it's just a mathematical identity. Then looking at this this second bit here, I also have that phi grad psi dotted into this this n hat object. So what is that? This is really the value of phi here, and then it's the derivative of the value of the function psi with respect to the kind of coordinate representing this thing. So for example, if I had a spherical thing, then the n hat vector would just be r hat, and grad psi dotted into n would just be d psi di. Okay, so that's just a kind of notation. So you see, we're doing the work of mathematical geniuses here, because we are really truly innovating, just plugging simple choices into simple equations, and we have achieved some absolutely totemic accomplishment here by obtaining Green's first identity. Okay, and what does that tell us? It tells us that the integral over a certain volume d tau of phi Laplacian of psi plus the grad phi dotted into grad psi, that this just becomes the integral over the surface dA of phi d psi dn. Okay, so that's the first identity of Greek. Okay, there's a second note, second one. C notes for the second identity. Okay, but what we're going to do is we're going to talk about uniqueness of solutions. Well, I don't think I'm going to make it in 1 minute, but so let's suppose we have two solutions to Laplace, phi 1, phi 2. Then I will define big phi as the difference between the two. Okay. So Laplace gives us manifestly that the big phi also obeys the Laplace equation like this. Okay. However, what I'm going to do, I'm going to use green 1 with phi is equal to psi is equal to this big phi. Okay, and what does that tell us? It tells us that the integral over the volume d tau of big phi, Laplacian big phi, plus grad big phi squared is equal to the integral over the surface dA of big phi with d big phi dn. Okay, and we're there. So this one is 0. Okay. Right-hand side is 0 if phi is equal to 0 or d phi dn is equal to 0 at the boundary. Okay, if anywhere at the boundary, either this or this is 0, then this whole right-hand side is 0. And in those circumstances, we would have that the integral over the volume of d tau, this term is manifestly 0, there just remains this one here, grad phi squared, would be equal to 0. And since this is valid for any volume V, it just means that the grad phi is 0. Okay? And this big phi is thus a constant. Therefore, the two solutions that we had only differ by a constant, which does not affect the electrical field. Okay? Which means there's only one solution. Okay? So maybe what we can do next time is we will state the uniqueness theorem very properly, but it will be based on this reasoning that we have in fact completed here. We've just shown that if you find a solution to the Laplace equation, you have actually found the one solution, and you will find this solution provided these boundary conditions are obeyed. But we'll codify that better next time. Okay.